Yeah, now we can see the Fibonacci sequence. Now it's okay. Can come.
Okay. So yeah, so the same thing happened a few weeks ago when I gave a talk for the conference, the Canadian conference. So I don't know why, but the Fibonacci sequence is defined by the recurrence here relation with the initial condition f0 it is 0, f1 it is 1. One thing we can notice it is if we consider alpha equal to 1 plus the square root of 5 divided by 2, and the conjugate beta, who are root of s squared minus 1 minus x minus 1 equal to 0, they define completely the Fibonacci numbers with the definition here, Fn, it is alpha n minus beta n divided by square root of 5. Now, there are some properties that we can notice. If we look at the definition of the sequence, we can rewrite into the form Fn equal to Fn minus 1 plus Fn minus 2. So that is the one remark. Another way, another identity we can notice, it is the Fn squared plus Fn plus 1 squared equal to F index 2n plus 1. Another that we can notice, it is just take from here, we take n equal to 3, and we can see that we have f3 equal to f1 plus f2. So it is the particular case where n equal to 3. Now, if we look all that, we can see that from there we can generalize and writing a Diophantine equation of the form fnx plus fn plus 1 x, and so on until f index n plus k minus 1 exponent x equal to fm. So the previous identity that we have seen fulfill this Diophantine equation, and the goal for the first results or the first paper we wrote is to try to solve this Diophantine equation. So coming back to the identity that I have shown, we can see that with the first identity, the solution of the Diophantine equation, it is 1, 2, and n plus 2. If we look at the second identity, this time x equal to 2 and k equal to 2, and we have m equal to 2n plus 1. For the last one, we have k equal to 2, n equal to 1, and of course, m equal to 3. I didn't put it here, but we can notice that x equal to 1. So we can also obtain another trivial solution that when s equal to k equal to 1 and m equal to n, we have also a trivial solution. So we are going to avoid the trivial solution, and here is the main result we obtain. The Diophantine equation, the only Diophantine solution of the Diophantine equation, I think the typo at the beginning of the theorem. So the only solution beside the trivial solution is the solution given by 6, 3, 1, and 3. So in the next part, I will try to solve. I would like to give a proof of the theorem, but it will be done in many steps. The first, to obtain the first step, I'm going to recall a few properties that we know. It is that if we take any positive integer, we can write the positive integer n into the form fm1 plus fm2 plus so on until fmk, with the condition mi minus mi plus 1 is greater or equal to 2, for I from 1 to k minus 1, mk greater or equal to 1. This is called the Zeckendorf representation of n. We will use that in our proof. Another thing that I'm going to remind the people it is we have what is called the prime divider theorem for Lucas sequences. So what it is said is that when m equal to either greater or equal to 12, fn has a primitive prime factor. It means that a prime factor p doesn't divide fm for m less or equal to n. So these two properties will be used in the first step. As I said in the proof, we will have many steps. The first step is to look at small cases. And if we consider k equal to 1 or 2, s equal to 1 or 2, so we use the Zeckendorf representation and the prime divider theorem to prove that the only solution it is given by 6, 3, 1, and 3. Okay. Then the second step it is to find an an inequality for m in terms of n, k, and x. So we use some inequalities that we can that are related to a Fibonacci number. It is if we look fn, we can bound fn by alpha n minus 2 and alpha n minus 1. And then we obtain, we use, if we take the log of both sides and we use some properties of a definition for the equation we have, we can prove that if we have any solution as k mn x, non-trivial, and with the condition k greater or equal to 3, s greater or equal to 3, because we deal with 1 and 2, then we can see that m is bounded by the two expressions here. We can notice that in this expression, we have the term n plus k. So that will be interesting because the next thing we will do will be to work with the term n plus k. Then we can try to bound x and m in terms of n plus k, like we have seen in the previous theorem. For that, we use Baker's method. To do that, we are going to use a linear form in logarithm, find an upper bound and a lower bound using a Matveev theorem, a theorem of due to Matveev, a kind of a modification of that. And we were able to see that if we have a solution k n m x non-trivial with the condition k greater or equal to 3, s greater or equal to 3, then we can see that s is less than the quantity, yeah, and m also is less than the quantity. So again, in the expression, you can see the term n plus k that will be useful in the future. The next step is to study the small values of n plus k. So we consider n plus k between 4 and 140. And if we look at the previous result here, you replace n plus k by the highest value, that is 140. And we can see that x is less or equal to 5.3, 10 to the power 16, and m is less than 1.3, 10 to the power 19. So this bound it is a little high, to use a computer to determine all the solutions. So what usually in this case, what we do is to use a reduction method. It is due to Baker-Davenport. We have new versions due to Tugela and Petrie. So we use that to find that our bound now, it is a little less than 171,000, no, 71,010. So with that bound, it is possible to run a program to solve entirely the problem. So that is what we have done. We consider n plus k between 4 and 140, and m between 5 and 71,010, with the condition that x is between 3 and 71,010 divided by the quantity n plus k minus 3. And we ran a program with Maple, and we prove that there is no solution in V range. Okay, so we deal with a small value of n plus k. We can look values higher than 140 now for n plus k greater than 1, greater or equal to 141. We look also x greater or equal to 16, and we try to bound the value of x. So we put like a condition s greater or equal to 16, and we use the Baker and the reduction method, and we came to the conclusion that there is no solution with the condition x greater or equal to 16. So we mean that at the end, if we have a non-trivial solution, we should have x less or equal to 15. The next step is to bound k. We deal with x. We deal with so we deal with x. We have a small value for x. We still have an n plus k greater or equal to 141. And in this case, we were able to prove that we can reduce the bound of k also to 115, not 13, I'm sorry. So that is for bounding. And the last step will be to consider k between 3 and 13, x between 3 and 15. And we said that t equal to the expression here, that is in the interval. So at the end, the t is between that. And what we have done is to run a program and see that we have no other solution. So we complete the idea about the proof. So after that, we ask ourselves, can we do with other sequences? So the next step was to look with the pair sequence. We know that the pair sequence is defined by the recurrence expression here. And we have also an identity here. And we consider a similar equation where we replace a Fibonacci number by a Pell number, and we obtain a similar result. And we see that there is no non-trivial, because we have some trivial solution. I said about the identity here. We have also trivial solution when we have s equal to k equal to 1 and m equal to n, and we can see that we have just a few trivial solution. And the main result say that there is no other solution for the Diophantine equation. The next step that we have done is to consider now a Padovan sequence. A Padovan sequence is the sequence, we call that the A here. Usually in the other paper, we call that the P, but all the other we have called P pair for pair number. we will put A here. So the sequence is defined by AN plus 1 plus 3 equal to AN plus 1 plus AN. With the initial condition A0 equal to A1 equal to A2 equal to 1. And we have done the same thing like we did in the first paper. And we consider the Diophantine equation here. And we prove that first, the first result is that we prove that what we can call the trivial solution the solution here, given here, the list here. So we have parametric solutions, except the particular solution here. So that is the first step. The second step is that we notice with identity here. That is the first. We have a second. And we prove the main result that beside the solution given by the previous identities, we have no other solutions. And that is the end of my talk. I try to recover the time we lost, and I hope you followed, and I will stop here. Thank you so much. Merci beaucoup.